We're doing the Lewis structure of arsenate and arsenite. Both arsenate and arsenite are analogous to phosphate and phosphite because phosphorus is in the same group of the periodic table, so it's going to have the same number of valence electrons. Whenever I draw a Lewis structure, I always recommend that you draw a T-chart where you catalog all the atoms that are in the molecule and you put an E minus to symbolize electrons. On the other side of the T-chart it says number of valence electrons. So arsenic has 5 valence electrons because it's a group 15 atom. Oxygen has 6 valence electrons and arsenate has 4 oxygen atoms, so 6 times 4 for the valence electrons contributed by oxygen. And lastly, you add a 3 because there's a charge of 3 on the arsenate ion. Total number is 32. So 32 electrons have to be accounted for in the Lewis structure of arsenate. We draw arsenic as the central atom. We connect each oxygen atom with a bond, and in the preliminary structure we're going to have 2, 4, 6, 8 electrons. When you use up 8 electrons, you still have, out of the 32, you're going to still have 24 to account for. So what I did is I wrote 6 electrons on each oxygen atom. There's 4 of them, so that uses up the remaining 24 electrons. Then what I do is I check for octets. Does this oxygen have a fulfilled octet? Let's look. 2, 4, 6, 8. Yes. So do all the other ones. They all have fulfilled octets. Arsenic also will have 2, 4, 6, 8. Remember, when you're counting octets, shared electron pairs are still count as 2. Then what we do is check for charge. Check for formal charges. When we check for formal charge, what we do is look at the number of valence electrons the atom has and then compare how many it actually has possession of. When you're counting charges, though, keep in mind that a bond counts for 1 because their shared electron pairs count for only 1. So we're going to say 2, 4, 6 plus the 1 here is a total of 7 electrons possessed by the oxygen atom, but it wants to have 6, and that's why we're going to write a formal charge minus 1 over here. The same applies to all the other oxygen atoms, so we end up with a total of minus 4 for all the oxygen atoms. Then when we look to arsenic, we find that it has possession of 4 electrons, but arsenic wants to have 5 valence electrons, so it's going to have a plus charge. Overall, this molecule would have a negative 3 charge because you have 4 minuses and 1 plus. But we have 2 formal charges, a minus and a plus, staring at each other across the bond. So that's not very likely to happen. What would more likely happen is that lone pair would end up becoming a bonding pair, and that would reduce the formal charge here to 0, and it would reduce that formal charge to 0. So what we have in the molecule, what Lewis structure predicts, is that this molecule will have 5 bonds shared over 4 positions. So we would have 5 over 4 bond character, meaning that each of these would be equivalent to 1 1/4 bond. And remember, the electrons are moving around there very quickly, so they're equally time shared. And that's exactly what you would observe in the scientific data for the bond strength of arsenate. You would find that it is equivalent to 1 1/4 bond, as the theory predicts. For arsenite, which is analogous to phosphite, again, arsenic has 5 valence electrons, oxygen has 6, there's 3 oxygen atoms, and then you add 3 more electrons for the negative 3 charge on the polyatomic ion, total of 26 electrons. This is the preliminary structure we end up with, and you'll notice that arsenic does not have a formal charge in this one because arsenic, again, wants to have possession of 5 electrons, and when you count the charge consideration, 2, 3, 4, 5, it does in fact possess 5 electrons. So there is 0 charge on the arsenic. Each one of the oxygen atoms has a minus 1 charge. So overall, the whole molecule, and you can symbolize it this way, has a charge of negative 3. And that's arsenite. Any questions? Yes?
I thought you only write the negative 3 outside it if you didn't put the negative charges inside it.
Yeah, you're right. You wouldn't, because that would look like it's a negative 6, I guess.
Yeah.
So you could show it like that. That would probably be a better way to show it. Overall, it's a minus 3 charge. But I think if you know how it works, you'll know that it has to be overall minus 3. So I typically don't do that to avoid precisely that confusion. I just show the individual charges on the oxygen atoms. You are right. I think you have to choose one or the other. Anything else? Yeah.
Sir, in arsenate, the second drawing you did,
Yeah.
how come it only has 2 minuses instead of 3?
Oh, because I forgot one. Thank you. minus 3 overall. And remember, when you do draw these molecules, you can draw what are called resonance structures to symbolize how that double bond is redistributed to all the other positions.
How many times would you have to draw the resonance structure?
Well, you'd have to draw, if you wanted to be really strict about it,
For all of them, right?
for all the possibilities.
Okay.
It's very time consuming, and
Would you want us to do
I
that?
usually don't demand that you do it
Okay.
except for a test,
Okay.
where, you know, you have to show that you understand that there is resonance. So I would draw the other one here. Okay, so each one of these has showing the negative formal charge. And actually, it's a little bit misleading when we draw all these things, because in actual fact, the molecule is time average of all of those 4 snapshots, so that none of these actually exists per se. What you have is these electrons whizzing around in there, 2/3 the speed of light. So you have 5 bonds shared over 4 positions. That's what it really means.
You draw the last one there.
I'll go the last one. I've done the double bond here,
Here.
there, so the last
Upright.
one is on the top right. That. So the molecule structure is basically a time average of all 4 of those structures. That's what we call resonance. And in fact, the more resonance structures a molecule has, the more likely it is to be a stable molecule, because it has more possibilities available to it, it has more degrees of freedom. Okay?